In this video, we're going to look at how to calculate equilibrium concentrations for a chemical reaction. So in some problems, you will be given the equilibrium constant, either Kc or Kp, and you'll be asked to solve for one or more of the equilibrium concentrations or partial pressures. You'll be asked to solve for equilibrium concentrations, generally if you're given Kc, and partial pressures if you're given Kp, generally. Now to solve these problems, there's actually quite a few steps involved. I've tried to break it into 10 steps. If you would, pause the video and write these steps down so that you can work these problems that we're about to go through before you see my solution. Okay. So let's look at our first problem. In this problem, you're given a chemical reaction. Carbon monoxide plus water yields carbon dioxide and hydrogen gas. And then you're given some information about the volume and the moles. Notice here that you are given the equilibrium constant and you're asked to solve for the equilibrium concentrations. If you would, pause the video and see if you can work this problem before I go through the solution. Follow those 10 steps and see if they help. Go ahead and try that. Okay. So our first step is that we want to set up an ICE table. An ICE table helps us keep track of the concentrations. We need to keep track of initial, therefore the I, change in concentrations, so the C, and equilibrium concentrations, so E. So we have our initial change and equilibrium concentrations here, and then we have our chemical reaction up top. Our next step, since we need concentrations, we need to be sure that everything is in terms of molarity in this particular problem, since we're given Kc. So we're given moles and volume, so we need to divide the moles by the volume in order to get our initial molarities. And again, these go in the initial column. We're not given any information about carbon dioxide and hydrogen, so we can assume that their initial concentrations are 0. So now we have everything converted into molarity, and we've inserted them into our ICE table. So the next thing we have to determine is what direction will the reaction proceed? Well, here we know that the reaction must go from left to right, from the reactants to products, because the concentration of our products is initially 0. So it must go in that direction. The reverse reaction can't occur initially. But it's important to appreciate not all reactions always proceed from left to right. So sometimes we'll have to go the other way. So we'll work some problems where that is the case a little later. Next thing, let's figure out our changes in concentration. The changes in concentration depend on the reaction stoichiometry. Here we have 1 mole of carbon monoxide plus 1 mole of water produces 1 mole of CO2 and 1 mole of hydrogen gas. We know the reaction proceeds from left to right, so these concentrations, the concentrations of reactants, will decrease. 1 mole, for every 1 mole of carbon monoxide that decreases, we will also lose 1 mole of water. So we have minus X over here because these concentrations will be decreasing, and we have plus X or plus 1X over here because these concentrations will be increasing. Again, if we had a 2 coefficient in front of, say, carbon dioxide, then this would be plus 2x, because for every 1 mole that we lose, we would form 2 moles of carbon dioxide. But again, in this case, everything is a 1-to-1 to 1-to-1 relationship stoichiometrically, and so our concentration of reactants will be minus x and products will be plus x. Again, these are only minus x and these are plus x because the reaction is going from left to right. If the reaction went the other way, from right to left, then the products would be minus x and the reactants would be plus x. So please keep that in mind. It's very important. Next thing, determine our equilibrium concentrations. Well, we can't determine those exactly, but we do know that our initial concentration minus the change in concentration will give us our concentrations, our equilibrium concentrations for the reactants. And for the products, it's going to be our initial plus X. So again, just X here. So our equilibrium concentrations are initial minus the change for reactants here, and our initial plus the change for the products. So now we have our equilibrium concentrations. And our next step would be to write our equilibrium expression, our Kc expression. Well, we should be able to do that without any problem. That's going to be our products over our reactants. So now we can plug in or substitute in our equilibrium concentrations. We must always just enter our equilibrium concentrations into an equilibrium expression, never initial concentrations. So we're going to plug these values here, even though we don't know exactly what X is, we'll be able to calculate that. So enter those into your equilibrium expression. We also know our Kc value. So now we have an equation that we can solve. So generally, when you solve this, we're going to use the quadratic equation. So you might want to familiarize yourself with that. In this particular example, we don't have to. We can take a little bit of a shortcut because everything on the right side is a perfect square, x squared over 0.02 minus x squared. So we can just take the square root of both sides and simplify our equation here. And then we want to get our x on one side, so we're going to multiply the left side by 0.02 minus x, and then we combine our like terms, our x's, and we should get x is equal to 0.00955. Again, if I went too fast there, feel free to pause the video and carefully review the calculations. Now that we know what x is, we can substitute it back into our into our ice table rather. So we have our x, and we're going to substitute it in to all of our ice table in order to find our equilibrium concentrations. So we can figure out the concentration of carbon monoxide, you see here, minus X, our concentration of water. All of these, again, are equilibrium concentrations, carbon dioxide and hydrogen. So now we have all of our equilibrium concentrations, and so our problem is solved. But it's always good to check your work, and we can do that because we know our Kc expression, and we know our equilibrium values, so we can plug those into the Kc expression. If we plug those into our Kc expression as solved, we get a Kc value of 0.83. We were given in the problem that Kc was 0.83 actually, and so those, well, that's exactly right. So now we know we had the correct answers. So let's try another problem. Read through the problem. Please pause the video and give it a try and see if you can solve for these equilibrium concentrations. Pause the video. Okay, so the first thing we want to do is let's set up our ice table. Again, initial, change, and equilibrium concentrations, and then our reaction up top. And let's figure out our initial concentrations. Those are given. They're already in terms of molarity, so we can plug those right in. Our HI, or hydrogen iodide, we can assume to be 0 since we're not given any information. Now, let's determine the direction the reaction will proceed. We don't have any product, so the reaction will always go in the direction where you have a 0. So if my 0 is over here on the product side, the reaction will go from left to right. Now that tells me that these concentrations of my reactants will decrease, and the concentration of my product will increase as it approaches equilibrium. So that helps us with the next step, determine the changes in equilibrium. We said it goes from left to right, so these must be minus x, and notice this is plus 2x because of our stoichiometry. Pay careful attention to your stoichiometry when determining the changes in concentration. 1 mole of hydrogen that reacts with 1 mole of iodine will produce 2 moles of hydrogen iodide, hence the 1x, and the 2x. Now we can determine our equilibrium concentrations. We just take our initial minus x, in this case for the reactants, and our initial plus 2x for the product, hydrogen iodide. Now we have our ice table almost complete. We can write our Kc expression. And once we have our Kc expression, we can plug our equilibrium values. Again, always it must be equilibrium values. We can plug those into our expression. And notice again, here is our concentration of Hi squared because we had the 2 there, divided by the concentration of hydrogen plus iodide to the first power. So again, be sure you're writing your Kc expressions correctly. Let's plug those values into our Kc expression along with the Kc value which was given in the problem. And now we can solve for x. In this case, as you'll see, we're going to need to use the quadratic equation. So in order to get the quadratic equation, we need to get everything in the correct format. I'll show you that would be here. Okay, so I've tried to get all my terms. So we have, again, pause the video if I went too fast there and review my calculations. But what we have there is we have our expression in the terms that we can use in the quadratic equation. Ax squared plus bx plus c. So 53, that's my a value. Negative 17.1 is b. And positive 1.14 would be my c value. And now we can plug those into our quadratic equation, which you can see here. Now you do want to be very familiar with solving these types of problems. So I plug in my a, b, and c values into my quadratic and solve. We always get two answers. So we get x is equal to 0.228, or it could be 0.0941. Well, which of those is correct? Well, let's take a look at our ICE table and see. If we take a look at the first term, the 0.224, let's plug that in here. If we plug it in for x, we're going to get a negative number. So we can't have negative concentrations, so it cannot be that first number, because if we use that first x value, it gives us a negative value. The second number must be the correct x value. So let's plug that in for our x, and we get the concentration of hydrogen is 0.1 minus our x. Our iodine, same thing, 0.2 minus x, and our hydrogen iodide would be 2 times x. So now we have all of our equilibrium concentrations. So we're done. We just want to check our work. So we can plug our equilibrium values into our Kc expression and solve. We get 55.6. We were given in the problem that it was 57.0, and that's pretty close. We know we did it correctly. We just rounded a little bit when we were correcting for sig figs, so these answers may not be exactly the same, but you can see here they're close enough that we know we've got our correct concentrations. Let's try one last problem. So take a look at this one, read through it carefully, follow the steps we've been doing. This one's got a little tricky, but see if you can solve this. Pause the video and give it a try. Okay, so let's follow our steps. Our first step, set up an ICE table. So we have our ICE table set up. Second step, insert our initial partial pressures. Here we're given partial pressures and Kp, so we put these in as atmospheres instead of molarities. Next step, determine the direction the reaction will proceed. Well, now hold on a second. None of my initial concentrations are 0. We cannot assume that the reaction will go from left to right. We have to check. If none of your initial concentrations are 0, so none of my initial concentrations are 0, I cannot immediately say whether it's going to go to the left or right. I have to calculate my Q value, in this case QP, and compare it to my KP to determine the direction. So again, review that section if you need to on how to use Q to calculate the direction of a reaction. But notice, if the initial concentrations, none of them are 0, you must calculate Q and compare it to K. So let's do that. It's not too bad. We can write our Q expression, which is the same as a equilibrium expression. These are just not equilibrium values. They're initial concentrations or partial pressures. We plug those in and we solve, and we get a value for our QP of 6.4. Now we can compare that QP value to our KP. 6.4 is greater than our KP, which was given as 0.338. Therefore, the reaction is not at equilibrium, and the reaction will proceed from right to left. So here, our reaction is going from right to left, from products to reactants. So not all reactions go from reactants to products. So that information is needed in order to calculate our changes. Because our reaction will initially go from right to left in order to reach equilibrium, Our products will be minus x, and our reactant will be plus x. And again, everything is a one-to-one stoichiometric relationship, so all our coefficients here are 1. So again, pay careful attention to those details. Now that we have our changes in concentrations, we can figure out our equilibrium concentrations, 0.16 plus x over here, and these initial concentrations minus x. Our next step is to write our equilibrium expression, in this case a Kp expression. Then we can plug in our equilibrium expressions into our Kp value, into our Kp expression, and also our Kp value was given in the problem. Now we have to solve using our quadratic equation. So we want to get everything in the correct terms. Ax squared plus bx plus c gives us equal to 0. So again, pause the video and look through those carefully if you got something different. So now we have it in the correct terms for the quadratic equation. Our a is going to equal to 1, our b is negative 3.248, and our c value is positive 0.97092. So let's plug those values into our quadratic, and then we solve for x, and we get 2 values for x. Only one of those can be correct. So let's plug our x values into our ICE table. And if we plug this first value into our ICE table, over here you can see if we subtract 2.9 from 0.14, we get a negative concentration. So we know that first one can't be correct. You can't have negative concentrations. So our x value that we need is this 0.33087. So now we just have to solve for our concentrations by substituting it in for x, and we get our equilibrium concentrations. So again, we're done. We just have to plug it in to our Kp expression, which we already have set up, and solve, and we get 0.359. Again, we do a little bit of rounding here to get the correct sig fig, so it may not be exactly, but that's pretty close, and we can see that those two values are in pretty good agreement. So there's a lot to these problems, but these are very, very important problems that we use a lot in our chemistry class. So please be sure to review these and work as many additional problems as you can until you get the hang of it.